All right. Yeah, they like sometimes show up late because there's a quiz. I don't know.
Right. So
I think it's gonna project like right now. So I'm broadcasting now.
I can get them started.
Hold on. So I'm gonna project. Yeah, I'm like taking it easy because like there's usually people coming in. Yeah.
That's okay. That's okay. It is Civ Bridge Week as well. That's exciting.
No, like they're done with the bridge. I think.
I think some of them still have to test it later in the week.
Did you test the bridge? Say again? Oh, there's no quiz. Okay. Oh, so people are just skipping. Okay.
It is close to finals. We'll give them the credit. Yeah.
Sorry.
Good to see you. A good turnout, all things considered. Yeah.
I would not say that. But... Hold on. All right. My friend.
Okay. Hello, 59s. You should know who I am by now. It's not for completeness. I am Abdullah. I'm a fourth year exercise 55 EY in the engineering physics major. And, as of earlier in September, I have the privilege of being the academics for Ensign Club. And so that is the capacity in which I'm here today.
I would do like midway, like here. Yeah.
Instead of like, yeah.
Yeah.
Okay, first and foremost, happy Civ Bridge testing week. I know some of you tested yesterday, some of you tested today, and some of you will be testing on Friday. Regardless, rite of passage, NSI iconic moment that you will walk out of, not the same as when you walked in for sure. It will give you stories of technical turmoil and great achievements for years to come. But I digress. I'm here to share the upcoming Engineering Science Club Fall Town Hall event. And as you can see, it's confirmed by the Clash of Clans Town Hall right there, in case there was any ambiguity. But it is essentially a once a semester event wherein all class reps across all years and myself, the VP Academics, gather in a shared space with reduced tensions and no problem sets in sight, and essentially just discuss at a high level how your semester has been. You are now approaching the end of your first out of hopefully many semesters in this lovely institution, and we'd want to hear more about number one, aspects of the curriculum that you feel maybe work better than others, aspects of the workload on the day-to-day on a larger scale that you felt maybe could be improved, cohesion between courses, deadline management, and everything in between. Doesn't necessarily have to be restrained to like academics, also just as a question of what you want to see more from Edgeside Club, what you want to see more kind of support in which domains. This is what this is for, and in general, I'm always advocating for as much first-year turnout as possible, because if anything, what you guys say now will have the potential to be implemented for first years in generations to come, and that's what this experience is all about. It'll be happening on Thursday in the evening, so 6:30 to 9 p.m. in the common room. I'm not gonna make you go far. I know most of you are there all the time anyway. And of course, maybe the first thing I should have said, pizza will be provided at no extra cost to all of you. I know the dietary habits probably aren't the best right now during Bridge Week, so I'm attempting to alleviate some of that. You should have received an email as of like an hour and a half ago from me discussing exactly what I just said, as well as giving you a link to an RSVP form should you want to attend, just so that I can gauge how many pizzas to bring. And with that said, you can definitely just like come on a rolling basis. You don't have to be there the whole time. Just let your voice be known, advocate your thoughts, and pave the way, blaze the trail for the incoming generations. Now, if you have any questions, please reach out to me. You know where to find me regardless. Fill out the RSVP form if you're planning on attending. And yes, good luck with the rest of your bridge testing, and good luck with the rest of the semester. Wishing you nothing but good things. You appreciate it.
Are you staying for the quiz?
I just might. See how much of it I still remember.
Yeah. You're staying for the quiz, right? Okay. You guys are all doing the quiz. All right. No. You got to do the quiz. I let you do the announcement. Hold on.
Oh, I'm doing the quiz? Sure.
Wait. Oh. I did not save it. Oh, yeah, okay. That is the quiz. It's available, right? It's oh. Okay, hold on. Sorry. All right. It's called quiz. I'm not sure why. Okay, save and publish. It is called quiz 10. Abdallah is doing question 1. What's the answer to question 1? Okay, what's the answer to question 2?
Lovely question. That's a lovely question. The answer is there, M log N. Tells you. I'm not gonna tell you the answer, don't get What's the answer? Yeah, first question.
He said yes. Yeah. All right. Who says A? Who says B? Okay, nobody's gonna say anything, I think. Who says C? Okay, someone says B. Who says D? Okay, revote. Who says A? Who says B? Yes, good. Okay, the answer is B. All right, thank you. I think you said that. All right, okay, thanks, Abdallah. Thursday, 6:30. So I was actually gonna do the football on Thursday. I guess I'll do the football on Friday. I'll announce that. So
Join us and then we can do the football together. So.
oh, that's okay. Let's like talk by email. Like maybe
Sure.
okay. Like maybe I'll do it on that day if you're okay with that. Okay, we'll talk by email. Okay, see ya. Bye. Okay, all right. Back to the material. All right. If you ask to make an announcement, that's what's gonna happen to you. So okay. So the algorithm was O of n log n. The answer, by the way, was B, if you're filling it out. So the algorithm was n log n, and what was given is that for n equals to 1,000, the runtime was, I believe, 100 seconds. 10. All right. So what does O of n log n runtime mean? It means that the runtime is approximately C times n log n seconds, where C is some kind of constant. Yeah. Yeah, you're right. Thank you. So C is some kind of constant, right? So what you're given essentially is just, it's a system of equations, right? So what you're given is C times n log n is 10 when n is equal 1,000. And you're being asked for n is equal to 1 million. What is C n log n? Right? So that's like the math question. Does that make sense? So O of n log n means that the runtime is proportional to n log n. So it's some constant C times n log n. And then you're given this, and you're being asked this. So it's kind of like solving a system of equations. So the only thing is that C is unknown, so you have to do a bit of a trick, right? So here's the trick. So the ratio of the runtimes for n equals to 1 million and n equals to 1,000 is C. So I'll write 1 million like this. divided by C like this. So that means that the C cancels out, right? So that's equal to 1 million divided by 1,000 times log 1 million divided by log 1,000. Right? So the C canceled out, so that's nice. We don't know C, but we didn't need to know C. 1 million divided by 1,000 is just 1,000. And then here, like there's like multiple ways of thinking about it. So one way to think about it is log AB is equal to log B divided by log A. So another way is to just compute this. So log base 1,000 of a million is to what power do you need to raise 1,000 to get a million? That is 2. And you can confirm that log 1 million divided by log 1,000 is 2. So that is 2. So the ratio is 2,000. So if it took 10 seconds and the ratio is 2,000, then the runtime is 20,000. Make sense? So that was kind of like the long algebraic way of doing it. How would you eyeball it? Well, you would just say, okay, so we are basically doing this ratio. So we're doing, you know, 1 million log 1 million divided by 1,000 log 1,000. And you kind of can say, okay, this is basically a little bit more than 1,000. And that's because n grows much faster than log. So if you eyeball it, basically the ratio is, about 1,000, a little bit more. As it turns out, the ratio is 2,000. You can do the exact computation. Does that make sense? So let's just do one more example. So let's say we have the same question, but the runtime is O of n squared. So let's say we're doing bubble sort instead of merge sort. What is the answer? So for n 1,000, the runtime is 10 seconds. What is the runtime for n equals a million? So it's 10 times what? I'm not going to tell you the answer. Talk to your neighbor about it. All right, who wants to risk it? 10 times what? Yeah.
10 times 10 to the 6.
Yeah, a million. Yeah, 10 to the 6. That is correct. Thank you for risking it. Hold on, here's the prize.
No way. Thought you're gonna get that. Thank you.
Okay.
Thank you so much.
Okay, all right. So the answer was 1 million. So how do I know right away? Well, it's 1,000 squared. So how do I do it in this way? I just say, okay, so the ratio of the runtimes is C times 1,000 squared divided by C times 1,000. Sorry. So C, this is C times 1,000 squared. So this is like C times 1 million squared. Divided by C times 1,000 squared. And this is 10 to the 12 divided by 10 to the 6. And this is 10 to the 6. Does that make sense to everyone? Yeah. So they kind of the way I would do it right away is I just say, okay, so it's 1,000 squared. So one last thing. So like the same question, but the runtime is O of n. 10 times what? 1,000, exactly. Yeah.
Thank you.
Okay. Hey. Yeah. Well done. Okay. Does this process make sense to everyone? Yeah. Oh, that's a thumbs up. Okay. Cool. Okay. All right. So that's kind of the intuition. So we are back to analyzing merge sort, which we've kind of done informally last time. And I'm just going to do it again. It's one of the more difficult derivations. So I think it's worth kind of doing it again because it was kind of fast last time. So to remind you, this is how it went. So we're saying, I think it's worth kind of revising it, even though we typed it in last time. I'm just going to type it in again. So if the list is shorter than 1, we're just returning a copy of the list. It's already sorted. Otherwise, we're merging the sorted version of the first half and the sorted version of the second half of the list. Okay, so that was the recursion. The idea, again, sort the first half, sort the second half, merge them together. We also need the merge function. And the merge function is, we're just going to say, so L1, L2 initially is 0, and we just have two sorted lists, L1 and L2. They're sorted. We are interleaving them so that we get a result that's sorted at the end. So I'm not going to repeat this. This is not like a super difficult algorithm, but I am going to type it in. If people have questions, let me know. So we're saying, do we append L1 at A1 or L1 at A2? And whichever one is smaller, that's what we append. So otherwise, we append L2 at I2. So now we've either appended all of L1 or we've appended all of L2. So we need to just append the rest. So I'll just do this. And then I'll do the same for I2. And I'll return the result. Is anyone not okay with merge? So I did it last time, but not everyone was here. I didn't know kind of what's the overlap between the people who were here last time and now. Is anyone not okay with this? If you're okay with it, I'm moving on because I did it already. So you can watch last time's lecture as well. Okay, I successfully bullied you into not asking questions. Okay, fine. Okay. So that's merge sort. That's it. And the magic is like, this is all it takes. This, like, it's kind of annoying to write, but it's really nothing, right? So, okay. So here is the analysis here. The analysis is we call merge sort with a list of length n. And then in each call, we say, I'll call merge sort with a list of n over 2, and then I'll also call merge sort with a different list of length n over 2. So that's going to be like this. And then here, when we're sorting the second half of the list, we'll call merge sort again with two lists of length n over 4. And so on. And over here as well. And that's going to go up until the point where we just call merge sorts on lists of length 1. And that just returns. So that is the call tree, right? So what we ordinarily did up until the point where we encountered this is we said, okay, like I'll just count how many calls there are. And the runtime is going to be proportional to the number of calls that they make. Here, that doesn't work. And the reason is that calls with larger L's actually take more time. The reason they take more time is that this merge function runs in time that's proportional to the size of the input, right? Like what this is basically you are building up a list result that's of size length L1 plus length L2. Building that list takes time that's proportional to the length of the list. The way you see it is, well, like you have like a flat while loop here, right? So how many times do all of those iterations run? Well, n times, where n is the number of elements in L1 and L2. Why? Because you're appending all the elements in L1 and L2, and that's all that you're doing, right? So this runs in time. So you could also say like O of length of L1 plus length of L2, but this is so like this is fine. If the question was like, what's the runtime complexity of merge? This would be the answer. But for the analysis, actually, this is more convenient. We'll see why, even like they say the same thing, but we'll see why in a second. So here's the strategy for the analysis. So we'll compute the runtime in total for this level. So for just this one call, and that's then for this level. So for this call plus this call, and then for this level, so this call plus there's two more here, and so on. That's not like a general strategy that works for everything. It just happens to work here. Okay, so here's how we're going to do it. We're going to say, okay, so merge runs in time C times length L1 plus length L2. So in other words, C times number of elements in the input. Right? So then we'll say, okay, so total number of elements is n. And then here, the total number of elements is n over 2 plus n over 2. So also n. And here it is also n. And here it is also n. Does that make sense? So it's kind of a trick. So we're saying in this call, there's just one call, and the total number of elements that are involved is n. And then here there's two calls, and the total number of elements that's involved is again n, just because this is n over 2, and then this is also n over 2. So that means that each level merge takes C times n time in total. Right? Does that make sense? So, great. Now we just need to know how many levels. And the answer is the levels go n over 2, n over 4, and so on down to 1. So log to n levels. So each level takes C times n time, and there is this many levels. So the total runtime is C times n log to n. So O of n log n. Make sense? So I want to go back to why I said that I don't like O of length L1 plus length L2. So the reason is if I'm not careful, then I won't get the idea that there is just the one constant here. So if I call multiple functions and all of them are O of n, and I do it k times, that does not mean that the total is k times n, because it might be that it's like 1 times n plus 5 times n plus 10 times n and so on. So here it was like more convenient to say that the runtime is proportional to this, and then to just specify, okay, the constant of proportionality is C, whatever it is. All right. So that is the derivation. So I should say, obviously, like it's not like so this is also in the handout. So this is not a super easy derivation, of course. It's technically, of course, like you'll see questions on the exam that are sometimes on this level, but that would be like the most difficult question on the exam that not many people get. So the basic complexity of recursive functions, like whatever, like if you do like the log example from last time, that's all log n, that you should know. This, of course, also you should know, but this is more like a big theorem that you have in calculus than like a small example that's going to be like question 2 in the calculus exam. Of course, no one here is going to solve question 2 in the calculus exam anyway, but let's separately from that. Okay. Questions about this? All right. So I have 15 minutes, and I want to do another. I can. Okay, this is the whole thing. You can do a screenshot from YouTube. So I want to do another thing, and I'm going to give out more prizes, not to you. You'll get away. Okay, so we're gonna play a game. So the game is called Race to 21. And this is not like waiting until you're legal to drink in the US. Yeah, most of you are probably not legal in Ontario either. Well, probably getting there. Okay. It's okay, you can build bridges instead. So it's the same effect on the brain, probably. All right. So here's the game. So we start with 0. And then each player in turn can say +1 or +2. First player to make the sum 21 wins. So a game might go like this. So we start with 0, and then someone says +1, and it becomes 1. And then the other person says +2, and it becomes 3, and so on. And whoever gets to 21 first is the one who wins. I need 2 volunteers to play the game, please. Yeah, so you in the back and you in the very back. Thank you. Come to the front, please. Okay, whoever wins gets 2. Hey,
I'm only gonna say the number 1.
okay, whoever guesses which has 2 starts. Yeah, so please guess. If you guess the hand with 2, then you start.
It's all in your hands.
Yes.
Okay, you start. Yes. +1 or +2?
Can I give up?
No.
1.
1,
+2.
3,
Wow.
4,
+2.
6,
1.
7,
+2.
9,
2.
11,
+1.
12,
1.
13.
1.
Hey,
Wait. 14.
1.
15.
2.
17.
1.
18.
Fuck.
Not a legal move.
1.
2.
All right, thank you very much. Okay, you get two, you get one.
you.
Thank you very much. Thank you. All right, so now that we know the game, let's make an artificial intelligence that figures out how to win. So, and like there is like a mathematical trick as well here where it's actually pretty easy if you know, but we are gonna do like brute force. How do I win? So what I'm gonna do is I'm gonna write a function. Gonna call it isWin. And what the function is gonna do is it's gonna return true if making it to n means you won. That's the function that I want to write. There is a very easy base case here, which is that if you say 21, then by definition, you win. So that's the base case. We return true. Okay, so now we got to do the recursive step. And the way to think about the recursive step is when do you start saying the F words when you see the N, essentially? So I did not make this up. That was someone else's initiative. So, okay. So, what's the F word is force, the A word is acceleration. Okay, so all right. Okay. So how do we do that? So we say, all right, so I win if my opponent cannot win. Right? So what does it mean? It means that I want to say whatever you do, you cannot win. How do I know that you cannot win? Well, I use the isWin function. So I'll say if you cannot win with n+1, and you cannot win with n+2, then I win. If I don't win, then I lose because someone's got to lose. So this I can rewrite as just return my opponent cannot win. That is basically it, right? So the way you think about it is the leap of faith. If my opponent is not winning, then I am. And the way to check that my opponent is not winning is if n+1 does not win and n+2 does not win, those are the only possible moves. Right? So that's kind of the basics of it. Let's debug it a little bit. So if I say isWin 21, that returns true. If I say isWin 20, that returns false. That makes sense. If I say isWin 19, that returns false. If I say isWin 18, that returns true. And the reason that returns true is that I say not isWin 20, isWin 20 is false. That makes sense. Not isWin 21, that returns false. So that makes 20, sorry. So that makes sense. So if this is like that, we can infer what isWin 17 is, right? So isWin 17 is not isWin 18. is when 18 is true. And not is when 19 is when 19 is false, is when 19 is false. So that doesn't work because is when 18 is true. So this is false. So 17 will return false. The logic here is 17 will return false because my opponent can then go to 18 and then I'm forced to lose. So if you know what the answer is to 17, 18, 19, 20, 21, well, you know what the answer is to 16, right? The answer to 16 is it's not the case that both of those are false. So that means that it's false. So here, this is false, this is false. So that means that 15 is true. And so on, and that works for everything. Does that make sense? So it shouldn't completely make sense. The way to do it is to think about it in terms of the leap of faith. The only way that they win is my opponent does not win. And if is when as a helper function works, then this is the formula. Does that make sense? So once you start looking at this, there is like a simple math trick where, so 21 wins, 20 loses, 19 loses, 18 wins, 17 loses, 16 loses, 15 wins, 14 and 13 lose, and so on. So the way to get the two chocolates is to name numbers that are divisible by 3. So that's like not super relevant to ESC180. That's just like if you ever get into this situation. Does that make sense? Okay, questions about this? All right, so we don't really have time for anything else, but if you remember the tic-tac-toe lab, what you did is you kind of like, you know, tried this, try that. This, if you go to the 2015 exam, that's, I believe, is the last question, is to basically do this, but for tic-tac-toe. You can do this, but for tic-tac-toe, right? So essentially what you do is you have a win condition. The win condition for tic-tac-toe, you actually wrote in the lab. And then here, what you're going to say is return my opponent does not win with any of the possible moves. So here, the possible moves were just n+1, n+2. In tic-tac-toe, the possible moves are place the mark on any free square. So, okay, I do have 3 more minutes, so I'll start rewriting this in a way that would make more sense for tic-tac-toe. It'd be very quick. So what I'll do basically is instead of like hard coding the possible moves, I'll say the possible moves are 1 and 2. And then instead of doing this, I'll say try every possible move. And I'll say if my opponent wins with this move, that means that I lose. If I did not find a way for my opponent to win, then that means that I win, so I'll return true. Does that make sense? It's the same logic here. Yeah.
So this is win function, it's only to see if you guarantee it. So
Yeah. So you guarantee, so are you guaranteed to win if you don't mess up? Yeah.
okay, so if it's like false, that just means like
the one that you may have a chance to win or no chance at all?
Well, yeah, I mean, like if you are like at 5, depending on what your opponent does, you might win or you might not win. This is, are you guaranteed to win if you play well?
Can I see this output is based on like just assuming that both people are smart enough to get.
So it's not both people are smart enough. This is assuming that the person we're asking about is not making mistakes. Right? So like in any kind of board game is so like there is a guaranteed outcome with perfect play, right? So here, so kind of in tic-tac-toe, it's guaranteed that it's a draw if no one messes up. And then sometimes if you have, you know, like 2 ways to complete a 3, then whoever has that is guaranteed to win. All right. Okay. 4 o'clock. I will see you tomorrow. Bye.